Sreedevi, IARE College, Hyderabad. Today I am going to give you a brief introduction to graph theory. Graph, all of you might have heard the terminology graph. What comes to your mind on hearing the word graph? It is a picture or representation of some data. It helps in visualizing the data properly that we are given. We all are using graphs in our day-to-day life. The main thing we are using nowadays is Google Maps, which is mainly on a graph application. We are using the networking of points. Actually, when said about graphs in mathematical point, it is a network of points connected through lines. And these points these points will be called vertices, and these lines will be called edges. Before going to formal definition, let's have a brief look at the history of graph theory. Graph theory evolved as a real-life problem. Actually, when it evolved was that it is part of graph theory evolved as a real-life problem. There was a river called Perigal, and on both sides of the city of Königsberg was situated on either side of river Perigal. Like this, both sides. And there were two islands of that city, let it be C and D. These four landmasses were connected with 7 bridges like this. Someone posed a problem whether it is possible to start from any of these land area and go through these 7 bridges exactly once and reach back to the starting area. That is, if you are starting from A, you have to go through these 7 bridges exactly once and you have to reach back A, starting point. You can start any of these landmasses. And the famous Swiss mathematician Euler showed it is not possible. And Euler is the first person to convert a real-life situation to this network of lines and a network of points and lines. And so Euler is termed to be the father of graph theory. And now we will be giving formal definition of graph. A graph G consists of a finite set of points. I am specifying P points, and finite set of points together with another set E of unordered pair of distinct points of V. What is this V and G? V of G and E of G. Yeah, we will say that if we are given some points, suppose V equal to A, B, C, D, and some E is the set, it is like that. It is defined to be the points in V such that there is some relation between that. If E equal to, if we are taking this AB, AC and AD, then how the graph will be? We have to plot these points A, B, C, D. So A, B, C, D. And it is unordered pairs where AB, we can draw like this AB, AC and AD. This is how it will be the graph. Okay. Here the P is equal to 4 and Q equal to 3. So once again, while we are considering this definition of graph, what it is? Graph is a finite non-empty set V equal to V of G of P points, and each one of which is called a vertex, together with a set E equal to E of G of Q unordered pairs of points, distinct points of V. Okay. This elements of E is called edges, and another name for edges is line, arc, branch, one simplex, etc. And these points of V are called But mainly we will be calling vertices. Some books you can see that it is points, node, junction or zero simplex. I hope now you are all familiar with the definition of graph. A graph with, if there were p points and q edges, then it is called, graph is also said to be g equal to pq. Okay. These p and q are termed as order and size of graph G. If G equal to PQ means G has P vertices and Q edges. This is order and size of a graph. When it is said to be, when we have already told that E equal to E means there is a point E such that E equal to UV. If it is like that, then we say that U and V are the endpoints of the edge E. It is also termed as the edge E is incident with the vertices U and V. Also, if there is an edge, because if E is an edge between the vertices U and V, so that we say that these vertices U and V are adjacent with each other. Similarly, for if any other vertices, suppose there are some vertices U, V, W, X and all, then we are saying that how these vertices and edges are adjacent. Please look at this figure. Here we have, please consider the first figure. Here we look at the vertices V1, V2, V3, V4 and V5. And I have just named the edges X, Y and Z between the vertices. X is between the vertices V1, V2 and V4 and Y is between the vertices V3 and V5. Z is between the vertices V2 and V4. Can we say that here, look in the first figure, it seems like that X and Y are adjacent to each other. In graph theoretically, they are not adjacent. Okay, because why? According to the definition, two edges are said to be adjacent if they have a vertex in common. Do these X and Y have any vertices in common? Just look at that. X, what are the endpoints of X? It is V2 and V4. What are the endpoints of Y? It is V3 and V5. So, is there any vertex common to both X and Y? No. So, they are not adjacent, though it seems to be adjacent. Actually, we can redraw the figure, first figure, like the second one. Now, you are getting better visualization that X and Y are not adjacent. Whereas X and Z are adjacent and Y and Z are also adjacent. So the edges are adjacent. How the adjacency of edges becomes, now I hope it is clear to you. Now we can see whether the vertices V1 and V4 are adjacent. No, because why? Because they don't have any edge between them. So they are not adjacent. Whereas V2 is adjacent to V4 and V2 is adjacent to V3. But V2 is not adjacent to V5. Okay? That is the adjacency. And we can say that edge Z is incident with the vertices V3 and V4. So I hope the terminology adjacent with, incident with, adjacency, everything is clear. Now let's see some other basic concepts that we have been using. I hope most of you are familiar with these terminologies: loops, multiple edges, multigraphs, pseudographs and all. What is this loop? We have already told that edge equal to UV, right? That is, edge E has two endpoints U and V. So if both the endpoints are same U, then the edge becomes a loop. That is, the endpoints, the edge is starting and ending at the same vertex. Then it forms a loop. Suppose we have a graph like this. And if there is an edge like this, this edge is termed to be a loop. That is, it is starting from and ending on the same vertex V1. Okay. Now multiple edges. If there is more than one edge between a particular pair of vertices, then those edges are termed to be multiple edges. Suppose between this V1 and V2, now we have only one edge. One line, matlab one edge. If we are drawing one more edge, like this. Now these lines, this one and this one form are multiple edges because these are multiple edges between the vertices V2 and V3. A multigraph is graph having multiple edges. This is a multigraph. Whereas a pseudograph is graph with multiple edges and loops are termed to be pseudograph. A simple graph means a graph without any multiple edges and loops. This is a simple graph. This is also a simple graph. And if it has 4 vertices like that, this is also a simple graph. Okay. Next, we will see what is a connected graph. You see that 2 vertices are connected if there is a path joining them. Can we say that this vertex is connected with any other vertices? No. But if it is like that, there is a path joining this vertex to some other vertex. Then we call that it is these vertices are connected. Suppose these vertices are like this. And can we say that it is a connected graph? No, because these 2 vertices V2, V4 are connected and V1, V3 are connected. But this is totally, it is not connected because we can draw like this also. V1, V3, V4, V2. This is same representation of this one. Okay, so these graphs are not, these vertices are not completely connected, whereas these vertices are connected. A graph is said to be connected if every pair of vertices are connected by a path. Every distinct pair of vertices are connected by a path, then the graph is said to be a connected graph. This is a connected graph, whereas the LI one which I have drawn like this is not a connected graph. Okay. This is disconnected graph. A complete graph then comes to the point of complete graph. What is complete graph? If there exists an edge between every pair of vertices. What is that? Because here we have V1, V2, V3, V4. Here we have, now it is a connected graph. Because we can find a path from V1 to V4, from V1, V2, V4. V1, this V3 can be connected to V4, V1, V3, V1, V2, V4. So there exists a path between these any pair of vertices. So it is a connected graph. We cannot say it to be a complete graph. A graph to be complete means every vertex is connected to every other vertex through an edge. This here V1 is connected to V2, V1 is connected to V3. We can make it complete by V1 must be connected to V4. And then V2 must be connected to V3 also. And this made a complete graph on 4 vertices. Okay. If it is on complete graph on 5 vertices, it will be like this only. 5 vertices. And first vertex is connected to every other 4 vertices. Then second vertex is connected to every others. Third one like that. Now it is a complete graph on 5 vertices. Such that a complete graph on, this is written as K5. And this is written as K4. When we are saying in general terms for n vertices, a complete graph on n vertices is written like that, Kn. Okay. Now we are going to the terminology. What is a degree of a vertex? Degree of a vertex means number of edges incident to that vertex. Here look at this figure. Here we have in V1, 3 edges are incident on V1. And here if it is V1, V2, V3, V4. Here in V1, 2 edges are incident on V1. So here degree of V1 is 3. Here degree of V1 is 2. And here degree of V2 is 1. Whereas here it is 3. Okay. So degree of a vertex means the number of edges incident on it. Suppose if I am having a graph like this with multiple edges there, on loop is also there. Then how the degree of this vertex, suppose if the vertices are named A, B, C, D, what will be the vertex degree of A? Yeah, it is 1, 2, 3, 4, 5 because when we are considering about this loop, it starts from A and ends in A. So it is adding degree 2 to the vertex which it is incident with. So the degree of vertex A is, now here it is 5. And what is about the degree of vertex B? It is about 3. What about C? It is 4. Okay. 1, 2, 3, 4. What about D? It is 2. So degree of a vertex is like that. Okay. Then if we have another vertex like this, consider this graph. I have 4 vertices. Okay. I am drawing like this. So is this a connected graph? No, because we don't have any edge connecting this vertex to the other part of graph, other set of vertices. So it is not a connected graph, it is a disconnected graph. And if what we will call this vertex? It is said to be isolated vertex. Isolated vertex. That is a vertex which is not incident with any other vertices of the graph. It is termed to be isolated vertex. Then we will see what is this regular graph. A graph is said to be regular if every vertex is of same degree. Because we have already seen that here, if it is a graph with 4 vertices, it is a graph with 4 vertices. Here every vertex is of degree 2. Okay. It is termed to be a regular graph. If every vertex is of same degree. Is it now a regular graph? No, because 2 vertices are of degree 3 and other 2 vertices are of degree 2. So it is not at all a regular graph. Now it has termed to be a regular graph of degree 3. It can be also said as a 3 regular graph. 3 regular graph. So it is when a graph is said to be regular of degree n, means every vertices are of degree n. So when we have learned about this complete graph, right? Just look at this. Is this a complete graph? What is the given graph a complete graph? Yeah, it is a complete graph on 4 vertices. It is Kn. Okay. This is K4. K4 of 4 vertices. So is it now what about the regularity of this one? It is 3 regular. So in general, a Kn is n minus 1 regular. I hope all these terminologies, stand terminologies, loop, multiple edges, multi-graph, pseudograph, simple graph, connected graph, disconnected graph, complete graph, degree of a vertex, and regular graph is okay with you people. Now let me move to other terminologies. Okay. Now we are going to see what is a directed graph. We have already seen that in definition of a graph, we were not dealing with the direction, only just the relation of incidence was preserved. Now we will be giving some direction. Suppose we have to start from a point and we have to go to some other point. Then we cannot just draw a line. We have to make sure the initial point and terminal point. In such cases, we will be making this directed graph. A directed graph or simply a digraph. It is also called, directed graph is also called a digraph. It consists of a finite non-empty set V together with some edges. And each edges will be assigned a certain direction. Here we are there in the definition of graph, we were using E to be an unordered pair of vertices, but here we are using ordered pair of vertices. Ordered pair of distinct points of E. The elements of E are called directed lines or directed arcs. Consider a graph, just this one, with vertices V1, V2, V3, V4 and V5, and the edge set is given like that. If it was in general graph, we will have been growing this, see here, V1, V4 and V4, V1. If it was in undirected graph, this will be of no use. V1, V4, V4, V1. The same line only. But here we have ordered pairs. So ordered pair means first one should be the initial point and the second one should be the final point of the line that we are drawing. Let's see how to draw this graph. We have points V1, V2, V3, V4 and V5. Okay. Now the first line is that V1 is joined to V2. So draw the line and just put one arrow. Okay. V2 is joined to V3. And then V1, V3. Okay. V4 is joined to itself. Means it forms a loop. And then V1 is joined to V4. Then V2 is joined to V5. Again V2 is joined to V5. Another line. That is multiple edge in the same direction. Then V3 is joined to V4. Then V4 is joined to V5. Then V4 is joined to V1. First we had V1 to V4. But here we are having V4 to V1 and the arrow goes in opposite direction. Then V5 is joined to itself like that. Okay. So it is the directed graph of given vertices V1, V2, V3, V4 and the given edge set. I hope you got the idea about this directed graph and have not a confusion in it. Thank you. Now we will move to the much more things on directed graph. In digraph, an edge is not only incident with a vertex but also incident out of a vertex and incident into a vertex, because we have in our drawing we have seen that V1 and V4. Regarding V1 and V4, there were two edges V1, V4 and V4, V1. So it is incident out of this vertex. This edge is incident out of the vertex V1 and this edge is incident into the vertex V1. Similarly, this edge is incident into the vertex V4 and this edge is incident out of V4. Okay. This edge is incident out of V1 and this is incident into V1. And this V1 is said to be the initial point of this edge E1, and this V4 is said to be the terminal line or terminal vertex of this edge E1. And this, for this edge E2, V4 is the initial vertex and this V1 is the terminal vertex. And if in this V4 we have seen like that. If V4 was the vertex, we had an edge like that, V4, V4. Then it is termed to be the self loop. That is a vertex having same endpoints. The number of vertices the number of edges incident out of a vertex Vi is termed to be the out degree of a vertex Vi, and it is written as d plus of Vi. The number of edges incident into a vertex Vi is termed to be the in degree of Vi, and it is termed to be d minus of Vi. And we will see how it is defined in this figure. Consider this figure with vertices V1 to V1, V2, V3, V4, V5 and V5 with edges E1. We have marked all these edges also. What is it? Consider this vertex. In general, if it was an undirected graph, suppose it was an undirected graph and no direction was given to any of the edges, what we will have written for the degree of vertex V1? It has 4 edges, 1, 2, 3, 4, 4 edges incident on this V1, and we will be writing d of V1 equal to 4, right? But now here we have given directions. Of the 4 edges incident on V1, 3 are emerging out of V1. So V1 is the initial point of 3 edges and terminal point of one edge. So what is this? We get this out degree of V1 to be 3 and in degree of V1 to be 1. Okay. So we can find the in degree and out degree of other vertices. When it comes to V5, see, there are 4 edges emerging out of V5. No edges are coming into V5. That is why this d minus of V5 is 0 and d plus of V5 is 4. Okay. Then we are going to some other important terminology called bipartite graph. What is bipartite graph? We all know this partition and all. And it is bipartite. Bi means 2. we are partiting two vertex set into two. The graph is said to be a bipartite if its vertex set can be partitioned into two subsets, such that no two vertices in one partite set is adjacent to other vertices in the same partite set. No two vertices in same partition are adjacent. Okay. A graph is said to be bipartite if its vertex set can be partitioned into two subsets such that no two vertices in same partition are adjacent. In general, if we can partite the graph vertices into m partite or m partitions can be made out of that, then the graph is said to be m-partite graph. Okay? That is, in a graph in which vertex set can be partitioned into a subset such that no two vertices in the same partite sets are adjacent. The subsets are also termed as partite set of a partition. This, when we are partiting in the groups, these partite sets are called partite sets. The separate partitions are termed to be partite sets. If in an M-partite graph, the vertices in one partite set is adjacent to vertices in each other partition, every vertex in other partition, then that partite set is said to, partition is said to be complete M partition. Now let us see this figure. Now we have these three graphs, right? If it is G1, and if it is G2, and if it is G3. Now consider G1. Here in G1 we have 8 vertices. We have how many ways we can partite? We can partite, put everything into different partitions. V1, V2, V3, V4, V5 and all. But is it required? No. Because we have to minimize the things and all. So when we are coming to partite sets, we can put this here. I'm going to put vertices like that. I'm going to divide the vertices and putting into different groups. Here I can put V1. Consider the graphs G1, G2, G3. In here G1, we have vertices from V1, V2, V3, etc. to V8. If I am going to put a partition to if I am going to bipartite the vertices of G1, how I can put? Let's see. I have just, bipartition means two partitions. So I am just putting two lines like this, two circles like this. First partite set P1 and P2. So how can I put the partite these things? If I am putting V1 to this partite set, can I put V2 to here? No, because according to the definition, V1 in vertices in same partite set shouldn't be adjacent. So I have to put V2 here. Then what about V3? V3 cannot be put in this partite set. So I have to put in P1. And similarly, V4 is put in P2 and V5 is put in P1 and V6 is put in P2 and V7 is put in P1 and V8 is put in P2. Okay. How they are connected? We can see that V1 is connected to V2 and V8. V3 is connected to V2 and V4. V5 is connected to V5 and V6. V7 is connected to V8 and V6. So is there any adjacency between the vertices in one set, the same set? No. In the vertices V1, V3, V5 and V7 in first partite set are not at all adjacent. Whereas they are adjacent to vertices V2, V4, V6, V8 in partite set P2. Also the same thing happens with the vertices in P2. V2, V4, V6 and V8 are not at all adjacent with anyone now. They are not adjacent with each other. Okay. Now we will consider this graph G2. What comes how we can partite these vertices of G2? Here look, the number of vertices is odd, right? V7 only up to V7. For how we can partite this? I am putting V1 in this one set, one group, and V2 in another group, right? Same way I am putting here V3, here V4, then I am putting here putting here V5, then here putting V6. Can I put V7 here? No, because V7 is adjacent to V1, right? Here, look at this. V7 is adjacent to V1. So can I put V7 here? No, because V7 is adjacent to V6. So I have to put V7 in another group. Okay. This is a tripartition of this set. So regarding this, when the vertices when in cycles, this partition can be made bipartite. The vertex set can be bipartite if it is even number of vertices, and if it comes in cycles of odd number of vertices, it is tripartition. And consider this graph G3. Okay, what is this? Here we have two partitions, first partition and second partition. The vertices in first partition P1 is adjacent to each and every vertex of the P2, right? This vertex is adjacent to four other vertices of this P2, and this also same. In this from P2 also it is happening the same. Then according to our definition, that is, if look at this, if vertices in a partite set is adjacent to all the vertices in other partite set, the graph is termed as complete bipartite graph. Here it is complete bipartite graph. So when it is coming to complete bipartite graph, we are using the terminology notation K24. If there are m vertices in one partition and n vertices in another partition, then we are writing as KMN. Okay? Now I hope this partition, bipartition, everything is okay for all of you. Now we will see a matrix representation of a graph. Okay? What is matrix representation of a graph? We have already seen graph to be a pictorial representation, and it is also good that pictorial representation is good for visual study. But this matrix representation makes the study of graph much more good in the terms of other terminologies in all connecting the algebraic terminologies and all. Okay, let's see what is the matrix representation of graph. Actually, it is good in the sense matrix representation makes good sense in the case of representing graph in computers. And also, it is good in the way of manipulating mechanical manipulations, and also it is good. Besides that, many non-results of matrix algebra can be applied to the structural properties of graphs. For graphs, we have different type of matrix representations like adjacency matrix representation and adjacency incidence matrix representation. Then we have circuit matrix, path matrix, fundamental cut set matrix, fundamental circuit matrix, and all. These matrices will be used in switching theory and all. Here, we are going mainly into the incidence matrix and adjacency matrix because each of it has much high priority in application. So, we will see how this incidence matrix of a graph is being defined. Let G be a graph with P vertices and Q edges and no self-loops. Okay, it can be a multi-graph but not a pseudo-graph. We define a P by Q matrix I equal to Xij, whose P rows corresponds to P vertices and Q columns correspond to Q edges. It can be defined as follows that Xij, that is element of this matrix will be that ijth element. What is this Xij means? Ijth element of this matrix I is if it equal to 1 if jth edge is incident with the ith vertex. If there is no incidence between this this jth edge is not incident with the ith vertex, it is termed to be 0. The matrix I of a graph is also sometimes written as Ig. Just to specify, it is related with the graph G. Now consider the matrix graph here. It is a graph with vertices V1 to V6 and the edges are named as A, B, C to H. Okay. So we will get how many 6 above, then we have 6 vertices and 1, 2, 3, 4, 5, 6, 7, 8 edges, right? 8 edges. So it is a 6 by 8 matrix. We have already, according to the definition, it is a P by Q matrix. So here it is a 6 by 8 matrix. And how the entries are, here look at this vertex V1. Which all edges are incident with this V1? D and F. So look at this. According to this, first we put this we name the rows with the vertices and columns with the edges. And for this first row, first column, that is first vertex V1, is it incident with is edge A is incident on the vertex V1? No. So we have to put 0 here. Similarly, B, C, but D is incident with this vertex V1. So we are putting 1 over here. And this F is incident with V1, and so we are putting 1. Other things are 0 here. Okay. Similarly, what happens with the vertex V2? Which all vertices are incident on V2? Here we can see that it is E, G, F and H. That is what we have put these ones here. And others are not incident with the vertex V2. So we are having zeros over here. In the same way, we can define this vertex. Look at this vertex. Which one? V6. Which all vertices are incident on that? A and B. And same with this. Is it with this V4? It is A, B, C, E. So A, B, C, E. Okay. It is how we can. That is, if we are given a graph, we can simply write this incidence matrix. And also, if we are given as incidence matrix, we can directly draw a graph. Okay. Now see how many ones are there in this row. It is 2. It gives, what is this? It gives the degree of the vertex, corresponding vertex. That is the rows, how many ones are there in particular rows gives how many edges are incident on that vertex. And also we can see that this in column, or in each column, we can see that there are only 2 ones. Okay. What does it mean? Because this edge A is incident with at most, an edge can be incident with a maximum 2 vertices. And that means, that is why these columns have only 2 ones in each column. In this matrix, only 2 ones in each column. And the number of ones in each row gives the degree of the vertices. Okay. I hope this incidence matrix portion is okay. Now we will be going to adjacency matrix. It is much more convenient way to express a graph. If a graph is without any parallel edges. Because here we are not approving. What all is not approving? Here graph is not without any self-loop. And now here we have self-loop also. Okay. Here self-loop is permitted in incidence matrix. Here parallel edges are permitted in this graph matrix. Here it is not parallel edges. Then we define the adjacency matrix A of a graph G to be AG equal to AIJ. What is this? AIJ is defined. How the entries in this ith row, jth column will be. It is 1 if the both vertex I is incident with vertex J, or adjacent. Adjacency matrix is a more convenient way to express a graph which doesn't have any parallel edges. If G is a graph of order n, then the adjacency matrix is written as A equal to Aij. And it is written to be an n by n matrix in such a way that Aij, that is element on ith row, jth column is 1 if ith vertex is adjacent to jth vertex. That means if vertex Vi and Vj are connected by an edge, we will be putting 1 on that place. Else we will not be putting 0 on that place. Consider this graph with vertices V1, V2, V3, V4, V5 and V6. Okay. Now we are putting the vertex names like this and here also. Okay. Now we see how this it is. So it has got a 6 by 6 matrix. Here we are using a 6 by 6 matrix because this graph we are considering has 6 vertices. And it is a 6 by 6 matrix, and look at the entry. Is V1 adjacent to itself? No. So it is 0. Is V1 adjacent to V2? Is it adjacent to V2? Yeah, V1 is adjacent to V2. So we are putting 1 here. And what about V1 and V3? They are not adjacent. We are putting 0. And V1 and V4 are not adjacent. Also we are putting 0 here. V1 is adjacent to V5 and V6. So we are putting 1s in this place. Same thing happens with V2. The same thing. Now we can see that this. Here also we can see that this place. It is V4, right? So is V4 adjacent to V4? No. So we are putting 0. If this place, V4, V6. Here V4 is adjacent to V6. So we are putting 1 there. And V6, V4. What about that? V6, V4 is also adjacent. So we are putting 1 here. Now we can see that this is a symmetric matrix. Symmetric matrix. Okay. And number of ones in each row corresponds, or each column corresponds to the vertex degree of the corresponding vertex. If there were some self loops, then what will happen? Suppose if I am having a self loop here, then this place will be replaced by 1. Okay. Do this parallel edges suggest the definition of this adjacency matrix does not permit the parallel edges. Okay. Parallel edges also termed as multiple edges. It is not suggested here. It is not permitted here in this adjacency matrix. Now what we will say, what is labeled graph? We already have, if we are drawing a graph like this, okay, have we defined and given any names to these vertices and edges? No. If it is not named, then it is called unlabeled graph. Suppose if I am giving a names to V1, V2, V3, V4. Now it is a labeled graph. Of course, even if I am not giving names to these edges, it is a labeled graph only. Because we can differentiate this. If it is E1, okay then. Else we can say that this edge to be V2, V4. This is also the edge name for this one. So if a vertex is named, then it is a labeled graph. Now consider this graph with 4 vertices and 1 edge. If it is unlabeled graph, see the first figure. If it is unlabeled graph, suppose there are 4 vertices. This one is same as this one. And this will be same as this one. So it is a graph with 4 vertices and 1 edge. Like this. This is a graph with 4 vertices and 1 edge. The same thing is here. But when these things are assigned labels, it has got different representation. That is, if you are putting that labels to be V1, V2, V3 and V4. This means it is our graph where there is an edge between V2 and V4. Okay. This means a graph having edge between V2 and V4. Whereas the other thing, it is different. When we were not given these labels, it is just a graph with 4 vertices and 1 edge. So labeling increases the number of graphs. Okay. I hope this is all. These are all different figures, a representation of, because V1 is connected to V2, V1 connected to V3, V1 connected to V4, and V2 connected to V3, V2 connected to V4, and V3 and V4 are connected here. Whereas this is the earliest representation if the graph was unlabeled or not labeled. And these are the different representations of a labeled graph with 4 vertices and 1 edge. Now we are going to the next terminology, subgraph, which is much more important in the study of graphs. A graph H is said to be a subgraph of a graph G. Before going to subgraph, I hope you are all familiar with the subset. Okay, a set is said to be a subset if it contains if A set B is said to be a subset of a set A if the elements of B belongs to elements of A. Here also the same thing happens. When we are considering the subgraph of a graph, H is said to be a subgraph if the vertex set of H belongs to vertex set of G and edge set of H belongs to the edge set of G. Okay, suppose we have a graph like this. A, B, C, D, E. And if I am naming the vertices edges to be E1, E2, E3, E4, E5, E6, E7. Okay. So if it is G, then I can draw a subgraph with vertices A, B, E like this. This is a subgraph with vertices A, B, E and edge E5. Okay, this is a subgraph of G with these vertices. This is also a subgraph of this graph G. Okay, this with vertices C, D, A, B, C, D, E. This is also subgraph of the original graph. Now I am going to spanning subgraph. If the subgraph contains all the vertices of the given graph, then the subgraph is termed to be a spanning subgraph. That is, here H, it contains all the vertices of G. It is a spanning subgraph. Suppose it is like this. This is also a spanning subgraph. Suppose I don't have this edge and this. This is a subgraph of the given graph, but it is not a spanning subgraph. Okay? Then what is induced subgraph? A subgraph is said to be an induced subgraph. There are two types of induced subgraph: vertex induced subgraph and edge induced subgraph. Okay, vertex induced subgraph you will see first. Suppose that if H has the vertex sets A, C, D. Okay, then we have to put like that. How we have to put? We are putting here A, C and D. If I am drawing like a graph like this, okay, if I am drawing like a graph like this, is it a subgraph of G? If it is like A, C, D, yeah, it is a subgraph. It is called, it is a trivial subgraph because it doesn't have any edges and all. It is a disconnected subgraph like that. So, it's a subgraph. But when we will say it to be an induced subgraph, we have this edge vertex set to be A, C and D. Is there any edge between A and C in the original graph? No. C and D we have. Okay. A and D? No. So it is the vertex induced subgraph. That is subgraph which contains all those edges which has its endpoints in whose endpoints are in the given set. Suppose if I am having this edge, vertex set A, E, D, B and D. Okay, A, B, D and E. How I can draw this graph? If subgraph A, B, E, D. This is the vertex set of the required subgraph. So I can have subgraph like this. Okay, it's a subgraph. Can I see it to be a vertex induced subgraph? No. Why? Because it should contain all those edges which are having endpoints in the given subset. So how can I make it a vertex induced subgraph? I should have this edge also. E1 should be there. E4 should be there. Sorry, E6 should be there. This E6 should be there. Then E5 should be there. E4, because anyone else? Yeah, this E7 too should be there. Then only it becomes a vertex induced subgraph. Now we'll go to edge induced subgraph. A subgraph is said to be edge induced. Suppose we are given a subset of vertex edges like that E6 and E5. I can draw this. E6 should be like that between E and B, right? And E5 is between A and E. So it is this subgraph is said to be an edge induced subgraph if we are given a subset of edges. That subgraph should contain the vertices which are endpoints of those edges. Surely it follows that a edge induced subgraph is a vertex induced subgraph, whereas a vertex induced subgraph, edge induced subgraph is a vertex induced subgraph, whereas a vertex induced subgraph may not be edge induced subgraph. Okay. Now we call the clique. What is this clique? Clique is said to be if the induced subgraph is complete, that is vertex induced subgraph is complete, then it is termed to be click. Suppose I have vertices A, B, E. If it is vertex into subgraph, then it should surely contain these edges also. Of which one? E1, E6 and E5. Okay, these vertices are contained, and so is it a complete graph? It is a complete graph on 3 vertices, and it forms a click of this graph, given graph. Suppose if I am having a graph like this. Suppose I am taking this vertices B, C, D and E. Okay. And I am going drawing this graph. Now this is a subgraph. Now it became a, what it became? It is an induced subgraph. Is it complete? No. So does it form a click of this original, does this subgraph forms a click? No. It is not a click. Whereas the earlier one was, this portion itself made a click. Okay. And now I hope you are okay with these terminologies. Subgraph, spanning subgraph, induced subgraph and click. Now we are moving to this graph. This graph G, and I have drawn as G dash. To this G dash is a subgraph of this graph G. No. Why? Because in G, do we have a vertex here? No. Right? According to this portion, we feel that it is a part of this. This has been drawn here, drawn to the second part. Is it so? No, because we are considering only these vertices V1, V2, V3 and V4. If we are considering these vertices V1, V2, V3 and V4, then okay. But here we have put another point. This is not a subgraph of this given portion, given graph. It is not a part of the given graph. Since we have taken only these 4 vertices. Suppose it is 1, 2, 3 and 4. And suppose we are taking 1, 2, 3, 4. Then what are the edges? If these 2 edges are not permitted in this subgraph, because the edges of the endpoints of this one, 4, 5, 6. This because the endpoint of this edge, it is 1, 2 and 5. Here we are not taking the 5 here. So this edge is not permitted. Also this edge is not permitted. So this is not a G dash, is not a subgraph of G, given graph G. Okay. What is this graph, subgraph, everything I hope. Now it is clear to you. Now we will see what is isomorphism of graph. In geometry, we all have learned about this congruence, equivalence of figures and all. Right from school days, we are all familiar with those things. So what we say that if they are congruent or equivalent, if they have some geometric properties, say. In the same way in graph theory, we say that 2 graphs are said to be equivalent. Here the terminology is not equivalent or congruence. We are using the terminology isomorphic. 2 graphs are said to be isomorphic if they have identical behavior in terms of graph theoretic properties. We will see what it is. That is, 2 graphs are said to be isomorphic if there is a 1-1 correspondence between the vertices and between their edges, such that the incidence relationship is preserved. That is, if there is an edge E1 in G1, which is incident with vertices P1 and U1, then the corresponding to E1 there should be an edge E2 in G2, such that we should find U2 and V2 corresponding to U1 and V1. Okay, how it is? Let's see. Consider these 2 graphs G1 and G2. Though they are looking different, they are isomorphic. How? Here, corresponding to this E1, we can find an edge 1 here. Please look at these endpoints of E1. Here we have this endpoint to be 1 and another endpoint of E1 to be with here one endpoint of edge E1 is with a degree 1 and another endpoint to be with a degree 3. Here also we can, to the endpoints of 1, edge 1, we can find the endpoints to be with degrees 3 and 1 respectively. Corresponding to each E1, E2, E3, E4, E5, we can E5 and E6, we can find edges 1, 2, 3, 4, 5, 6 respectively. Okay. Except for the labels of the vertices and edges, isomorphic graphs are same and can be drawn differently. Look this. It looks, all the 3 graphs looks entirely different, right? 1, 2 and 3. These 3 graphs looks entirely different. But these graphs are isomorphic. These are 3 isomorphic representation of the same graph with 10 vertices and 15 edges. Look here, and also this every vertex is of same degree. Here also same degree, here also same degree, here also. Okay. Now we will see much more how these things will be. From the definition of isomorphism, it follows that the isomorphic graphs must have same number of vertices, same number of edges, equal number of vertices with a given degree. Here we have seen that here one vertex with 1 degree and here also 1 vertex with 1 degree. Here 1 vertex with degree 2 and here also 1 vertex with degree 3. And other 3 vertices are of degree 3 here. Here also we have 3 vertices of degree 3. Here also we have seen that equal number of vertices with same degree. 10 vertices of degree 3 here. Here also 10 vertices of degree 3. Here also 10 vertices of degree 3. Okay. Any confusion in it? No. So the same thing follows from the definition, that same number of vertices, same number of edges and equal number of vertices with a given degree. But is this conditions proper for a graph to be isomorphic? Here see 1, 2, 3, 4, 5 edges, 6, here also 1, 2, 3, 4, 5 edges, 1, 2, 3, 4, 5, 6 vertices here, and second graph 1, 2, 3, 4, 5, 6 vertices here also. And also a number of vertices with same degree. Here also 1, 2, 3 vertices of degree 1. Here also 1, 2, 3 vertices of degree 1. And here is one vertex of degree 3. Here also one vertex of degree 3 in this figure. Here 2 vertices of degree 2 each. Here also 2 vertices of degree 2 each. But can we say that these graphs are isomorphic? No. Why? Because look at this vertex x of the first graph. Here x is adjacent to 2 vertices of degree 1 and 1 vertex of degree 2. Okay. Corresponding to this vertex, we should find another vertex y in the second graph such that it is of degree 2. Degree 3. Here we could find one y here. Now look at the adjacencies of y. Y is adjacent to a vertex w with degree 1 and other 2 vertices of degree 2. That is, it is called, so this, we cannot find a relation between this x and y. Okay. If it is drawn like that, 1, 2, 3, 4, 5. This, if it is G1, then G3. This G1 and G3 are isomorphic. But G1 and G2 is not isomorphic to each other. Also, if you are drawing like this, this is also isomorphic to G3 is isomorphic to G1. But G1, this is not isomorphic to this here. Okay. So, according to this, we should completely follow that 2 graphs are said to be isomorphic if there is 1-to-1 correspondence between the vertices and between their edges such that the incidence relationship is preserved. This should be main part of considering the isomorphism of 2 graphs. There should be a 1-to-1 correspondence between the vertices, there should be a 1-to-1 correspondence between the edges, and the incidence relation 2 should be preserved. Okay. Now I hope you all are okay with the terminologies that we have discussed here, just like from the basic definitions, like basic definition of graph, from the terminologies that we'll be going to deal with this loops, multiple edges, multi-graph, pseudo-graph, simple graph, connected graph, disconnected graph. And connected graph, it means we should find a path between every pair of vertices, distinct pair of vertices. But in complete graph, there should be an edge between different pair of vertices. Okay? And degree of a vertex, isolated vertex, that means a vertex which is not connected to another vertices. That is isolated vertex. And suppose if there is one vertex like that, such that its degree is 1, and we say that it is called pendant vertex. Those things we will go in detail to next slides. Okay, next portions we will go. And this in degree and out degree of a vertex of a directed graph. Then what is bipartite graph and what we have impartite graph and complete impartite graph. Then we have seen what is matrix representation of a graph. We have dealt with incidence matrix and adjacency matrix. Now, what is label graph and what is the difference in labeling? Okay. And subgraph, spanning subgraph, induced subgraph, and clique. And then the isomorphism of graph, which is most important. You should be familiar, which is called this. It should be always kept in mind that incidence relation has to be preserved. I hope all these terminologies are okay for you. And next video we'll meet again. Bye. Thank you for watching. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.